So let's talk about this r squared. We already talked about r, which is the correlation coefficient, which can be between -1 and 1. And the closer it is to -1 or 1, the stronger the relation if we're talking about a linear regression. Now, r squared is telling us this important question. We want to find out, and I'm going to write it up above here. We want to know how much, or in other words, what percent of the variation in y, so a variation in the response variable, is described by the variation in x. Or in other words, described by the line. So that's what we're trying to figure out. So in terms of thinking about, there's two terms we want to define. First of all is the total variation in y. So the total variation in y, well, that's what thinking about how does the different y values, how do they differ from the mean? So that's going to be our, if I try to squish this down here, that's going to be the errors, how does it vary again from the mean? So that's going to be our SST. And again, that's our total variation in y. And how SST is calculated, you're just taking all the data points and subtracting from the mean and squaring. So y1 minus y squared plus y2 minus y hat squared plus y3 minus y hat squared all the way to the last one. So I'll just calculate it as yn minus y hat squared. So that's the total variation. Well, how does the variation in the least squared regression line compare to that? So, in the variation in the least squared regression line is our SSE. So the SSE is basically the sum of our residuals squared. So it's going to be, instead of comparing it to the mean, we're comparing it to the predicted value. So it would be y, the actual value, so I'm going to say y1 minus y, the predicted squared, plus y2 minus the predicted squared, plus y3 minus the predicted squared. So the difference is just doing the sum of the residual squared, in other words. So yn minus y hat squared. So, and that's how good, so that SSE, the sum of the squared residuals, if that's small, that's saying, wow, this line is pretty darn accurate. So we want to figure out, so one thing I think that might be helpful is thinking about how much of the variation in y, so how y is changing, is not described by the line. So to figure out how much is not described by the line, the least squared regression line, we would figure out, okay, what is this SSE compared to SST? So in other words, what is the sum, the variation in the residuals, or the sum of the square residuals? What is that? How does that compare to the sum, the total variation in y? So in other words, this is saying, okay, what percent is not described by the regression line? So to figure out what percent of the variation is described by the regression line, it would be 1 minus that. So that's what we're getting at here. So in order to figure out what percent of the variability in my response variable is due to variation or variability in the explanatory variable. In other words, how good of a predictor are we dealing with my least squared regression line, would be 1 minus the standard error of residuals over the total variation, the y minus y hat squares, those summed up. Okay, so let's see about what various things mean here. So let's go to, unfortunately, I numbered this pretty poorly, but there's a second 4 here. We already did a 4. What does SST equal 0 mean? Well, this simply means that, so if the total variation of y is 0, it means that all y values essentially equal the mean. So all y, I'm going to just say y sub i's equal y bar. So all the data value, all the y values equal the mean. Unlikely. What about SSE equaling 0? Well, that means that all values of the response variable are perfectly predicted by the least squared regression line. So all the predicted values equal the actual values. Again, very unlikely. What does SSE equal SST? So total variation versus the variation in this residuals here. It means that the errors resulting from the regression equation are equal to the errors when y hat is used as a predictor. So using the errors from the least squared regression line is the same as using the errors from the mean. Okay, so what are the bounds on r squared? In fact, what can r squared equal? Well, r squared can equal anything from 0 to 1. So it's, there is the predictor SSE, if SSE equals SST, again, unlikely, but if it does, then your r squared is being 0. And if SSE over SST is 0, then it's going to be 1. If r squared is a value close to 1, what can you conclude? Let's go to the next page here. Well, if it's close to 1, then we're going to say that the linear regression equation produces errors that are much smaller than the errors generated by y hat as a predictor. So a good chunk of the variation in y can be explained by the variation in x using the least squared regression line. If r squared value is close to 0, what can I conclude? The errors generated by using y hat and y bar are essentially equal. So using one versus the other doesn't matter. So usually the default is you just use the mean if that's the case. Okay, so in the last two, you just want to, these last problems here, or I guess it's just one problem, you just want to get at what does the r squared mean. And so first you're going to find the r squared in part A, and it should be about 0.66, in which case you're going to say when you interpret it, and this is always going to be the way you interpret it, you will say 66% of the variability in the price of the Ford F-150 truck, again, context of the problem, is explained by the variability in mileage. And we're going to do more practice with this next class.